So this is a generation question, electricity generation. And what we've got for this question is we've got a loop of wire here, which is being dragged through from position 1 to position 2 to position 3, between these two magnets here, between the north and the south pole of this magnet. Connected to this is a sensitive micrometer, ammeter, so that is just to measure the current that makes. So because we pull from here, which is outside the field, there's no field out here, to inside the field to outside the field, we change the flux. And a changing flux produces electricity. What this picture here is this is the same picture as here, but this is looking at this loop from here. So it's like we've got our man here, here's our happy face, he's looking that way, and he sees, remember the field lines go from north to south, so he sees field lines coming at him, so he sees field lines coming out of the page. So those are dots coming out of the page. Alright, so there's only field lines here, and then the loop is completely out of the field in position 1, and position 3 it's out of the field as well. So what's the first question asking us? Which of the following graphs best shows how the flux through the square loop varies with time as it moves from position 1 to position 2 to position 3? Well, before we even start looking at what the possible answers are, we see here there's no field lines. Now flux, we'll use a green, flux is equal to the field lines through the loop times by the area. At the moment there's no field lines through the loop, so in position 1 there's nothing, no flux. Flux equals 0. Position 3, flux equals 0 as well. It's out of it. And in here we've got the full amount of flux. Now just to make this easier, think about what the flux is doing here in the loop. There's probably half as much flux, and when it's in this position here, again there's half as much flux because these field lines are all the way out here in this box here. Okay, so 0, a bit of flux, full amount of flux, bit less flux, and 0 again. The only one that really fits that is this one here. 0 flux, getting more flux as it goes in. It's all the way through this, in between the magnets, and then decreases as it's on its way out. So that's that decrease as well, and then there's 0. This is the only one that really fits that position. So in this case, we've got A. Alright, let me just open up the next one. Alright. Which of the following graphs best shows how the EMF in the square loop varies with time as it moves from position 1 to position 3? So the EMF is the voltage made, and there's a formula for that, Faraday's law. EMF equals, we'll leave the negative out, negative change in flux over change in time. Now for those of you who are doing methods or have done methods or specialist maths, you'll know change in flux over change in time, this is a gradient of a flux time graph. And guess what? In question 8a, we just had a look at a flux time graph. And our flux time graph in question 8a looked like flux, time, and it looked like flat, up, flat, down, flat. So the really hard thing is to look at this and say, how does the gradient change? The gradient in this first section is nothing. It doesn't rise at all. The gradient here is 0. No rising gradient. Where else is it 0? Well, it's also 0 here. The gradient is flat. Remember, gradient is rise over run, and it doesn't rise at all there. So gradient 0 in that bit, and the gradient's also 0 and this bit here. So we're looking for a graph here where the gradient, where the value out of these three graphs starts off as 0, does something is 0, does something is 0 as well. This starts off as 0, does something is a high number, does something is 0, so it's not this one. 0 goes up to a number, 0, not this one either. Remember we're trying to equate the gradient of this to a value here. This has a value of 0, has a value of some high number, and a value of 0. It doesn't, we're looking for a value of 0, in the middle of value of 0, at the end of value of 0. Not this one either. This one has a value of 0, a value of some high number, then a value of 0, a value of a negative number, a value of 0. This one's looking good, but we'll just check it out. So we've had a look at these three easy points here, the gradient of the three easy points. We're looking at the gradient. What about between here and here? Well, the gradient in this case is positive. It's some positive number. And the gradient here, the rise over run, is going down and it's a negative. And it's the same here. This gradient here is the same as the gradient here, is the same as the gradient here, the same as the gradient here. And that's why it fits this. We've got here a gradient of 0 here, equates to a value of 0 for this first section. We've got a positive gradient equates to some positive number here. We've got a gradient of 0 equates to a gradient of 0. We've got a negative gradient equates to some negative value here. And we've got a gradient of 0 equates to a value of 0 here. So this is our answer for this one. D. Alright. Now describe the last question, describe the direction of the current in the square loop as it moves from position 2 to position 3. So let's just recall, I've put the picture up the top here, this is the picture from the previous page just to make it easy, again, that we've got our field lines going north to south, which means they come out of the page here. Because this is going from position 1 to position 2 to position 3, the flux is changing, we make a voltage. Because it's a nice loop here, the voltage, electricity can flow, and we make a current. So this question is asking us the direction of the current. Whenever we see these direction of currents in electrical generation, this is a Lenz's law question. Lenz's law. And a lot of students find Lenz's law very difficult. We're only looking at this one from position 2 to position 3. From here to here. Which direction does the current go from position 2 to position 3? And just so you're not scared about Lenz's law, because people find it really difficult, they're really asking, does the current go anti-clockwise or does it go clockwise? So in the end, our answer is only going to be anti-clockwise or clockwise. It's just the process that gets there that some people can find a little bit difficult. So Lenz's law is something along the lines of a loop will produce a current which will give rise to a magnetic field which will oppose the original change in flux. Now again, that sounds very, very complicated, so I like to simplify it, and maybe you might want to simplify it as well by having something like this on your cheat sheet, which I'll write down the bottom of the question and I'll cross out afterwards because the examiners might not like it too much, but it's my translation of Lenz's law. So translation of Lenz's law, and it is, I liked the flux the way it was. This is going to help us step through this question. I liked the flux the way it was. We can cross it out later. Now, this is a 3-mark question. They want to describe, so there's going to be 3 dot points for this. Right, so let's write out our answer. in black. First dot point. So Lenz's law says a current is produced which gives a magnetic field to oppose original change in flux. That's our first dot point. So this is Lenz's law that you're going to have on your cheat sheet. And then we're going to go back down to our translation to help us get the rest of these answers. I like the flux the way it was. We're going from position 2 to position 3. So how was the flux? How did it like it? Well, if you look here, these red dots coming out of the page, the loop liked having field lines coming out of the page. It liked the way it was. It liked having those field lines coming out of the page. So it now, in position 3, doesn't have any field lines, but it liked them coming out of the page. So, according to Lenz's law, or my translation of Lenz's law, because it liked it so much the way it was, it's going to make those field lines the way it was. So it's going to make its own field lines out of the page. How does it make field lines out of the page? We're going to use the right-hand solenoid rule to do this, and in that our thumb points in the direction of the field lines and our fingers are the current. Well, if you take your right hand and point in the direction of these field lines come out of the page, so you take your right hand and point out of the page, you find that your fingers curl around anti-clockwise. In this case, anti-clockwise. My fingers would curl around in this direction here. So that's the way the current's going to be made in this situation. Now I just have to write it up to make sure I get the full marks for it. So my second one says, carrying on, Lenz's law says a current is produced which gives a magnetic field. The current is anti-clockwise. And this produces a field out of the page which is opposing the change in flux. So I'm just going to go over this just one more time, just for 30 seconds, just to make sure we understand this. My translation says, I like the flux the way it was. It liked having field lines out of the page, so it's going to make its own field lines out of the page because it doesn't have them out of the page anymore. To do that, I use the right-hand solenoid rule, which says that the current is going anti-clockwise. The way I write this up is I take actual Lenz's law, which I'll have on my cheat sheet. It says a current is produced which gives a magnetic field to oppose the original change in flux. I've just worked out the current is anti-clockwise because this produces this field coming out of the page, and the flux had been changed from out of the page to nothing. So it's going to oppose that change, i.e. it's going to go back to the way it was, and this is why I write this last point. It produces the field out of the page which opposes the change in flux.